Yeah, so I'm going to probably use the book as more of a guide than I usually do in class because it knows where it's going,
Right.
and the science is about to show up. Okay, but we should probably we'll reset a few facts as we go. Okay. So I'm going to just go sequentially through the book. We're in chapter 1 at 1.8. And 1.8 is a reiteration of what we already know. I think it's already been on the board, that there's an electromagnetic spectrum, and visible is here, and I have the low energy non-ionizing radiations here, and I have the high energy ionizing radiation here, which is the X-rays and the gamma rays. And I have ultraviolet. So ultraviolet's the region that we're really interested in. This is just enough energy to dislodge electrons. So this is going to do what it says it's doing. It's ionize. It's going to ionize our materials. These are so high in energy that they dislodge things in a slightly different way. And down here at the low energy where I've got radio, this isn't important to us. Okay, so we're looking here at the very high end of the visible light into the ultraviolet, and we're going to see how it interacts with matter. Okay, so there's two equations, and they've already been on the board today in another class. They're coming back. The speed of light is the constant that holds together wavelength and frequency. Speed of light is 3 times 10 to the 8 meters per second. And lambda is wavelength, and nu is frequency. Okay. Wavelength being exactly what it sounds like. Write a wave, find a place where that wave repeats. The length, the distance between those two places, is the wavelength. If you have a static place in space and the waves pass you, how many cycles per second did the waves come by? That's the frequency. So wavelength is in meters, frequency is in cycles per second, which then gives us speed as being meters per second. Okay? Makes sense. That's the first one. The relationship between frequency and wavelength is underpinned by the speed of light, which is a constant. And we've talked in other classes about not thinking about constants as numbers that are used in an equation. Constants are the thing that holds all of the other information together. It's the speed of light that contains all of this information. I'll leave it this way. It is so hot right now. The other one is that the energy of our electromagnetic radiation is equal to Planck's constant multiplied by frequency. Now, our book has already told us it's a wavelength book. It's not a frequency book. It's a wavelength book. It's going to measure everything in wavelength. So what we have to do is rearrange this top one and substitute wavelength in for here. So energy, this H is Planck's constant, and then frequency. Energy is in joules, frequency is in per second. Hertz is another way of saying cycles per second, which means that Planck's constant is in joule seconds. And C is 3 times 10, it's 2.99 something or other. 9979. Yeah. Times 10 to the 8 meters per second. And Planck's constant is really, really tiny. 6.626 times 10 to the negative 34 joule seconds. Okay? So, wavelengths are inherently easier to understand because I can say 400 nanometers, I can say 11 centimeters for the wavelength of a microwave. Whereas frequency is just a jumble of numbers. Okay. So what we're going to do is I'm going to substitute that value out. All right, I'm going to rearrange C equals lambda nu in terms of nu. If C equals lambda nu, what does nu equal? Take the lambda, move it across the equal sign. It was a numerator, becomes a denominator when you move it across the equal sign. So nu equals C over lambda. So this guy, E equals H nu, now can be rewritten as HC over lambda. All right. Well, H is a constant, and C is a constant. These two numbers are fixed. E is 6.626 times 10 to the negative 34 joule seconds, multiplied by, do you want to give me, because this has got precision, it's 2.998 times 10 to the 8 meters per second, all over lambda, which is going to be in meters, okay? So this per second and that second are going to cancel out. This meter and that meter are going to cancel out. It's going to leave me an answer in joules. What is 6.626 multiplied times 10 to the negative 34 multiplied by 2.9999?
119,627 kilojoules. 19627 is what the book gave.
119,627. 119,627. Just a number divided by lambda. Okay? So if I know wavelengths, I can put an energy to it. Typically, in the past, we've done this of just kept these two. We use wavelength to find frequency, then we use frequency to find energy, because the energy to frequency relationship is a direct relationship, and that's just easier for first year students, early students to grasp. This has now got a reciprocal relationship. It's in inverse. That what's the higher energy, the big wave or the little wavelength? Little wavelength. If I divide by a small number, I have less impact on my big number on the top. If I divide my big number by another big number, I make my total energy be smaller. Okay? Short wavelength, high energy. Long wavelength, low energy. This is going to start to appear now in terms of if we look at bond strengths, enthalpies of dissociation, is the light from the ultraviolet spectrum powerful enough to cause that dissociation? Okay. That's where our book is heading, because we have an ozone layer that has relatively unreactive oxygen in it, and if we hit it with ultraviolet radiation, perhaps we can initiate something meaningful out of that. Okay. So when enthalpy finally shows up, and it's just about to show up, we will revisit. I'm going to keep this on the board because we'll come back to it a couple of times. The energy of an event is 119,627 divided by the wavelength of the radiation instigating that event.
Wouldn't that be joules?
It's going to be in joules, yeah. What do we know about joules? It is a measure of energy. Do we remember anything at all about how many of them even the simplest thing requires? Yeah, it's always quoted in kilojoules, which tells us that the joule is a very, very small quantity. Joule is a really small quantity, and in order to do anything meaningful, in order to make even like a temperature change, you're going to need thousands of joules. So when these numbers come back, and wait a minute, so I put them into my calculator, and the calculator tells me it's 500,000. That can't be right. Well, actually, yes it is, because 500,000 is 500 kilojoules, and that might be on the scale of an enthalpy for a chemical reaction. Okay. Okay. All right. So on page 14, it says, well, it's kind of putting the cart before the horse, because yeah,
14.
okay, no, it's fine. It's fine. Ozone is an allotrope of oxygen. All right, let's go back. This is one of the things that we said in our preamble of, this is basically just a refresher of all the chemistry that you need. Dioxygen is a non-polar diatomic molecule, homonuclear diatomic molecule with a double bond. This makes it reluctant to react with other things. And although it does these really high profile reactions, combustion, very, very high profile reaction, and respiration, which is also a kind of, on paper, it's the same as a combustion. It's wildly abundant, which means it's stable. You know, again, you'll pick an argument with people if you tell them that oxygen is stable, but it is. It's 21% of the Earth's atmosphere. That double bond means it's going to be difficult to split it. If we go ahead and split that into two oxygens, there is a heat energy change associated with that. Delta H's are enthalpy changes. No matter how many times you hear me or anybody else say the word enthalpy, we always mean enthalpy change. Enthalpy change just means heat. How much heat did it give out or take in? And the value for this is 498,000 joules. 498 kilojoules. Now, our book, there's a decimal place there, there's also a point for. Let's write that down because we will be using this number. Our book doesn't do something that I want it to do. Can you guess what it is?
They didn't tell you they're equating for
No, I just mean about this number.
Oh.
There's something I would like it to do with that number that it hasn't done. But it doesn't know what I want.
The number of decimal places.
Oh, yeah.
I would like that to state for the record that it's a positive value. Now that's redundant, you don't need it, but energies, as we say 100 times during chemistry 1 and 2, general chemistry, energy has a magnitude, that's how big the number is, and a direction. Is it coming in or is it going out? When the value is positive, what does that tell us?
It's exit. Right, exit.
If in doubt, take a pause and think about the logic. You have something, how have we described this? Stable. And now we're breaking it apart. Does that sound like it is taking in energy or giving out energy? This is taking in energy. If you have a positive, I'm going to put that in a box, so when we get to use it, we get to use it. This is a positive enthalpy change. And positive enthalpy changes are endothermic events. This reaction is taking in taking in heat, energy. You have to spend energy to make this happen. Okay? If you are spending energy on this reaction, you are spending energy on this. What does that do to you? This is the reaction. You are the surroundings. We're only talking about heat exchange, we're not talking about any mechanical work. Not yet. This is the reaction. You are the surroundings. Together, you're the universe, you are the system. Okay? The system is the reaction and its surroundings. You are the surroundings. You have to give this reaction heat, energy, in order to make it work. What does that do to you?
Lose heat.
You're giving away heat. What does that do to you? It makes you cool down. This reaction takes in heat from where? From the surroundings. Where's the thermometer? In the surroundings. This makes things get cold. And there's a little explanation in the book about, hey, at the lower atmosphere, that's where the weather is, in the troposphere, and the sun shines on the earth and it heats the earth up, and the earth has heat capacity and the oceans have heat capacity, and they take in heat during the day and then they let that heat go, water very slowly, but solids, rocks and sand or whatever, fairly rapidly, and you get these big convection currents, and you get a big mixing of temperature in the atmosphere. But as you go higher, you don't get that. You don't get that. The sun isn't impacting on anything solid. You don't get those convection currents. You're now too far away from the convection currents because of gravity. And you start to get, when this reaction happens, it makes the air around it cold. And so we got this little temperature inversion where things were warming up and then they get cold and then they warm up again. All right, this is an endothermic reaction. It takes in heat. It has a positive value of enthalpy change. It makes the environment colder. I'm going to use two words that mean the same thing. It makes the surrounding environment cold. And then cold air and hot air. There's a density difference between those. And that density difference could cause mixing, but it's as equally likely just to cause the cold air just to form a band. And so where this is happening, it settles into a band in the atmosphere of, I've got a little band, a little layer of cold air, okay? And the temperature above and the temperature below are higher temperatures. In fact, we showed that in an earlier graph. The temperature goes up, it goes down, it goes up again. Okay. All right. So there is oxygen. One thing that I haven't seen the book do yet, but we should think about. Okay. Oxygen, group 6, has 6 valence electrons. Dot, 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 dot. Each of these oxygens has 6 valence electrons. When I split this bond, or both of them, I'm going to do what's called a homolysis. This is a homolytic cleavage, where it's 2 of the same thing. And this goes 1, 2, 3, 4, 5, 6. I have 2 oxygen atoms. We don't see oxygen atoms at ground level because an oxygen atom has 2 unpaired valence electrons. All right, let's unpack that. What are valence electrons? The ones on the outside of the atom. On the ones on the inside, they're called core electrons. core electrons are not involved in chemistry. It's only the outside of the atom that interacts with the outsides of other atoms, and so only the outermost electrons are responsible for chemistry. And we know that oxygen has 6 total electrons because it's in group 6 on the periodic table. The periodic table is our big cheat sheet, and we look at it, we find oxygen in group 6. So we count out 6 electrons for it. And we go 1, 2, 3, 4, and then we start having to pair them up, because we ultimately want to get to 8, the magic number being 8. So oxygen has 2 unpaired valence electrons and 4 electrons in what we call non-bonding pairs of electrons, or lone pairs of electrons. Okay? It's only the unpaired electrons that are available for covalent bonding. That's a lie, but it's a textbook lie. Okay, so these ones, unpaired electrons, now makes you reactive. There's a word. Oh, it's lost forever. There's a word that some of you have heard. This is a very reactive chemical, and it's very reactive because it has an odd number of electrons. This doesn't have an odd number of electrons, but having an odd number of electrons guarantees that you have unpaired electrons. What's that called? If you have unpaired electrons.
Lone pairs? Wait, no, I'm sorry.
Called radical. And radicals are insanely reactive because they have these unpaired electrons. And electrons want to be paired. One of the fundamental things about chemistry, bond theory, is if you have unpaired electrons, they will find a way to pair themselves up. So this, in the absence of anything else, really wants to get back to being this. And we know that because the reverse reaction of 2 oxygen atoms becoming 1 oxygen molecule would just turn that sign from being a positive to being a negative. And you'd give out 500,000 joules, 498,000 joules of energy if you did the reaction in the opposite direction. Okay? All right. So we've turned something very, very stable. We know it's stable because the atom on the left has 8 valence electrons and the atom on the right has 8 valence electrons. It has this closed shell, full octet. It's done. But we've scythed those two bonds and made 2 reactive atoms instead. Okay, that's how far we've gone. Let's go explore why this is being mentioned, and do we have enough energy to make that happen? Okay, so the next statement is, you'll remember from general chemistry that you can find the enthalpy of a reaction. Remember this? The enthalpy of any reaction can be found under standard conditions. Do we do standard conditions in this book? Yes, we do. Under standard conditions. Okay. If you perform all your experiments under the same set of conditions, you can write all those values down in the same table and then share them with colleagues all around the world who have done the same different experiments but under the same set of conditions. And all of your numbers work. So it can all be tabulated. It's a great big appendix at the back of the general chemistry book. Or you go online and find these values. Okay? What are standard conditions?
290 degrees Kelvin,
Yeah, so
or 25 degrees
the
Celsius.
chances are that the experiments are done on a bench top in a lab somewhere at room temperature. And room temperature is 25 degrees Celsius, which is 298 Kelvin.
1 atmosphere.
The pressure inside the room is also 1 atmosphere. And what if you do something in solution? One mole per liter. Okay. Under standard conditions, the enthalpy change for any reaction is equal to the sum. Do we understand what sum means? Just add the numbers together. Of the enthalpies of formation at standard conditions under all the number of moles. There's a little n there. This is the number of moles. How many of them do you have in the equation? There's a 1 here and there's a 2 there. Of the products minus the sum of all the enthalpies of formation of all of the reactants. Okay. Well, delta H is the change in heat energy, the enthalpy change, for a reaction under standard conditions is equal to the sum of the number of moles of the enthalpy of formations under standard conditions of all the products minus the sum of all the number of moles of the enthalpy of formation under standard conditions of the reactants. So we need to define what this is. This is called the enthalpy of formation. Do you remember how we know what the enthalpy of formation means? The enthalpy of formation is the energy, heat energy. We need to be specific. So enthalpy of formation technically is enthalpy change of formation, but every time you hear anybody say enthalpy, it's always an enthalpy change. Is the heat energy either gained or lost when the product is made from its elements. Okay, so if I was making carbon dioxide, I would need carbon and oxygen. I would need 1 atom of carbon and 2 atoms of oxygen in order to make one molecule of carbon dioxide. If I was making ammonia, NH3, I would need 3 times as much hydrogens as I have nitrogens. But I'm going to make the product from its constituent elements. In the naturally occurring form. Okay? So, if I was making occurring 1C, 2 Rs, 2 Cs, 1 R.
Yeah.
Yes.
That's right.
Yeah, it's one of those words I write wrong and then correct.
Wait.
Yeah.
No.
Wait, is it a double R? Wait.
It's two.
It's
C's
definitely
on
2
R.
C's, yeah. Well, now, yeah.
Yeah. Yeah. 2 Cs.
No.
It's 2 C's, 2 R's.
Is it really?
Yeah, it is.
Okay.
Oh, that's bad. I should know how to do that. It's like
All right.
say a word and nothing sounds
So
funny.
let's throw a few things at this. If we're making carbon dioxide, I need 1 atom of carbon and I need 2 atoms of oxygen. The naturally occurring form of carbon, graphite, like you're using in your pencil. It's a solid. And then I need 2 atoms of oxygen, which I would find in oxygen's naturally occurring form, O2. And I would take graphite and gaseous dioxygen and stick them together, and they would make carbon dioxide, and the energy either gained or lost in that reaction would be my enthalpy of formation. And if I did it at room temperature, at 1 atmosphere, and if I used a solution and I made it be 1 mole per liter, then I have a standard thing. Okay. Now, caveat. Let's pretend for just a second that I wanted to make oxygen, O2. Just pretending, just for a second. How much energy is that going to cost me or gain me? Under this definition. If I wanted to do a reaction where at the end I made O2, this is my target molecule, that's my product, and by definition the way to make it is to find the element in its naturally occurring form. Oxygen in its naturally occurring form already is O2 as a gas. We haven't been putting our state symbols in. Gas. Gas. How much energy is this going to cost me? Nothing at all. It already exists. The delta HF for elements is nothing. They already exist. You gain nothing, you lose nothing. They already exist. Okay? So, that means, look at this. I need a tiny bit of space here. This means that if I look at this particular reaction, the enthalpy change for the reaction is 498.4 kilojoules. And it is equal to the enthalpy of formation of the products. Got to multiply it by the number of times it appears, minus the enthalpy of formation of the reactants. Well, look at our reactants. Our reactant is elemental oxygen. So this value is 0. It is 1 times 0. The value here is 2 times delta HF of O. Okay. Which tells us, let's just flip this around. Let's take that 2 and put it over here. And it's not going to be a numerator anymore, it's going to be a denominator. This tells me that the enthalpy of formation of O as a gas is 498.4 kilojoules divided by 2, which is,
249.2.
yeah, 249.2. Nope, I don't need the line. Okay. All right. Well, it turns out that this guy has a big role to play. And that's why we've bothered to take a look at it. Okay? So the what have I done wrong?
You didn't put positive.
I didn't put a positive here, because this is a 10-point quiz on paper. You got, for all of this, you got 9. You got 9 out of 10. Enthalpies are energies. Energies have a magnitude and they have a direction. This is 249.2 thousand joules of energy being taken in order to split oxygen into O, and each individual O is worth this much. 2 of them together is worth this much. 2 of them gives you that number. 1 of them gives you this amount. Okay? All right.
I have a question.
Yeah.
On the middle part, or the first part where in red Sharpie,
Yeah.
why is it only 0 at the end? Because the n equals the number of moles, right?
Yeah. So
So it
1
would be
times
1.
0. Yeah. I did actually say that out loud, but I didn't write it down. Yeah, so this bracket belongs here, that bracket belongs there. There is one of these, so it's 1 times 0. And it's 0 because of this. Look at that. Oxygen already exists. It's not benefiting you, it's not detracting from you. It already exists. It costs us no energy to make. It benefits us no energy being released. Okay? All right. So we're going to go investigate a couple of things, but I want to actually skip ahead a tiny bit. So we're currently on at the bottom of page 14. I want to just put this into context. At the bottom of page 19, there's a cycle. And it says, well, what are you going to do with that individual oxygen atom? And then we'll throw a few things around and see what happens when you go forward and see what happens when you come backwards. And then we'll see where this comes in. We left it on the board for a reason. Okay. So, I know why the book didn't do it straight away, but sometimes you need to, if I'm going to watch your 12-minute video on how to make lasagna, you've got to show me in the first seconds that you're making lasagna. I'm not going to sit through you collecting all the pieces together, and then only find, oh, it's a lasagna in minute 10, right? I need to know up front. Here's oxygen in the gas phase. We're going to do something to it that makes it split apart. That process is called dissociation and become oxygen. Oxygen atoms. And then we're going to add another molecule of oxygen, dioxygen, and make ozone. And then there are two ways back. This is a cycle. I can go this way, from here to here. Whenever we do this kind of cycle, what we tend not to do, and there's a reason for this, in other branches of chemistry that make sense, doesn't make any sense in this one, but just to be consistent, we typically don't do that. Straight line, hard shoulder. We usually put a curve in it that tells you, hey, this is flowing. It doesn't matter. To go from ozone back to oxygen, ozone itself is going to be unstable. It's O3. We're going to figure out that, at the end of today, maybe I'll time it. Remember Lewis structures? We had one on the board for oxygen, dioxygen already. Try to do the Lewis structure for ozone. Is it in the book?
No, I just remember it from.
Yeah, it's problematic. Yeah.
What is it? It's a strained? It's a,
Oh, if you made it be,
wait, a strain. Oh, wait. I made it a ring.
and there is a question of why is ozone not a ring, and it's because of the strain.
Okay.
Yeah, it's not a ring, it's something else, and that is itself very, very problematic. We'll kind of do that at when I recognize I'm running out of time.
Okay.
We'll leave this as a hanging thought that you can go away and investigate. Because what we've got, this is stable. This is unstable. Now this is also unstable. But probably not as bad as that. And if you give O3 an individual O, it sees the opportunity to make two O2s. Okay? And then there's another way where this just undoes itself. And we lose an oxygen and we go back to just being O. And it turns out that the prompts to make these things happen. So what you would do, in going this way, if I'm gaining oxygen going forward, our book doesn't write this, but I'm going to write it this way. You lose oxygen on the reverse. You're giving this oxygen away, putting this oxygen in, giving this one away. Okay. We haven't proven it yet. We have to come back and prove this. But ultraviolet light is going to split oxygen. And then ultraviolet light is also going to split ozone. It's one of the benefits. But they're different bands. This is C, and that's B. Let's find the little table from earlier that tells us what those bands are. UVC, UVB, UVA on this table give us that.
UVC is up to 200 and 280.
Yeah. So I'm going to do UVC, UVB, and UVA in reverse order. What's the range for C?
200 up to 280.
Yeah. In units?
Nanometers.
That's in nanometers, and we spent a little bit of time earlier reaffirming that we all know what a nanometer is. 10 to the negative 9, 1 billionth of a meter. And UVB?
It's 280 to 320. Nanometers, and then 320 to 400 nanometers for
Okay.
UVA.
All right. Of these three, C, B, or A, which is the highest energy wave? C is the highest energy wave because it has the lowest wavelength. Our book, and I can't blame it, has opted to go with wavelength over frequency. Wavelengths are easier to understand than frequencies. But what it does mean is when the number gets smaller, they become more dangerous. Small numbers equals more danger. Shorter wavelength. Okay. So, when you put the high energy radiation in, you do the dissociation. This is called a dissociation. And this is the high energy ultraviolet. This, oh, this has got a, no, actually, yeah. This is also a dissociation of types, but this one is equal, right? We take a thing that is two things stuck together, and we just split them apart. This one's going to be unequal. We go from something that is high, it's got 3 atoms, and we break it apart into 2 smaller things. So I think I would rather call that a decomposition than just a dissociation. I don't know what our book calls it. I haven't read every single word. I've just read every other paragraph. Let's call that a decomposition. There's a couple of fabulous words that I don't know that we're going to get to see. They're called disproportionation and comproportionation. Disproportionation is when you have something in the middle and it breaks apart and makes something bigger and smaller than itself. And a comproportionation is when you have something big and something small and they get together and make small. No, it doesn't work. It doesn't work. Okay. All right, let's go figure out. We already know the answer. Let's go figure out if it's true. So we're back to page 14. We're going to do E.
They call it decomposition.
Do they go? Then I was right. I always like it when. Okay, let's ask ourselves a question. Pens 498.4, no?
Yes.
What wavelength of light is capable of splitting dioxygen, O2? All right. E equals HC over lambda. Four, 9.8.4 kilojoules is equal to 119,627 all over lambda. Just switch these values. Just do a diagonal swap. Lambda equals 119,627 divided by 4. No, I should do it down here, shouldn't I? Good math. 498.4. Boom. Got another? Other people find their own way.
Yeah. 240.1.
Okay. We could probably keep the 0.1. Is there really a 0.1 here?
I got .02, I don't know.
Did
that-
you go?
Yeah, I don't know, I mean, I also transpose my numbers all the time, so I don't always
Okay,
take it.
so our answer is 240 nanometers. We are owed, I mean, we are allowed to have a decimal place here, but it sounds like it's a 0. Okay, that puts us, this number is there. That's the UVC, that's the high energy UV band, right there. Okay, we did something, look at that. All right. Let's do the reverse. I think we know what the answer to the reverse is, or at least we have a sense of it. Let's do, what wavelength of light will no. Do it again. I was going to use accomplish. Let's just say cause. Will cause ozone as a gas be converted into dioxygen as a gas and monatomic oxygen as a gas. And the enthalpy for that conversion, that's this step right here, that one in this loop, that is plus 105.
Can we get that number from the book?
Yep. It's hidden deep in the, you have to squint to find it. Because our book writes calculations as streams of text. It does highlight the important passages in this lovely blue color. Is that blue or green? I can't tell.
Green, teal.
Yeah, I have no idea what blue and green are. I'm not blue-green colorblind. I just don't know what they are.
Is this blue or green?
It does highlight stuff, but because it saves space with the way that it writes, it throws numbers into paragraphs. Okay? Yeah. Temperatures and conversions, it is literally
Yeah.
6 or 7 degrees Celsius hotter
I feel like I'm
this
going
spot
through ozonolysis over here.
than 2 liters to my right. It's a big temperature gradient there. All right, what we got? Let's work it out. HC is this number, and that number E is 107. That's all I got, right? There's no 105. No decimal, just 3 digits. Kilojoules. Do the reshuffle. The lambda is 119, no, not point. 67 divided by 105 gives you a value of,
I know, 1.94.
You did a decimal, I think, instead.
Oh, yeah, that.
yeah, that's not a point. My bad, that is
I did that initially too.
that is
I was like, that's not right.
a comma. You know, different civilizations, different nationalities have, some of them use the comma as a decimal point. It's very confusing. Some cultures, you know, we group everything in multiples of 3. So we have thousands and millions and billions. Some cultures oscillate, that the commas are sometimes between 2 digits and sometimes between 3. How do you expect me to work with a system where there's no continuity? Yeah, the Indian currency market is bonkers. Nobody knows how much money they've got because they don't categorize things. All right, what we got now?
Big number.
Yeah, 1,139.
Is that right? That's not right.
No,
That's what I got. I got too.
0.3. Seems very big.
Well, they don't have an answer. I do have an answer. I have the solutions manual. Let me see. The delta, so the question, problem 1 and 2. The delta H for the decomposition of ozone into O2 and atomic oxygen is plus 105 kilojoules per mole. Oh, I was about to talk about this. Why are we just saying kilojoules and not kilojoules per mole? Because the reaction is this, bump, bump, bump. We got lucky. This is a 1 and a 1 and a 1. And if you tell me, our book just told me, 105 kilojoules per mole, my question to you is, per mole of what? I ask the same question where I take nitrogen and 3 hydrogens and make 2 ammonias, and I say its delta H is 1,000, completely making the number up because I can't remember what the value is. 1,000 per mole. Per mole of what? Per mole of this, or per mole of that, or per mole of this? Because that's a 1 and that's a 3 and that's a 2. When we talk about reactions, we don't say per mole. We just give the energy amounts. There is no per mole. Bad textbook, naughty textbook. We don't do that because we lose track of, well, what do you mean? No, the energy change is for the reaction. It belongs to the reaction, not to the... Okay, so there is a typo, isn't there? Because we know, or we think we know, that the it's supposed to be in the UVB band. So my guess is that's the wrong number. I think I printed the wrong number in the book. You must Google.
I don't have this. I don't see that number. What page?
It's at the bottom of page 15. As I said, it's difficult to
Oh,
find.
yeah. Wow, they really did have that hidden, didn't they? All right, so decomposition of ozone.
Can you just press it?
Mhm.
Did I bring my phone? No. Yeah, I think that's all right, let's do it.
Yeah, it's so decomposition of ozone is plus 105 kilojoules per mole.
Okay, all right. And the answer comes out to be 1139.3 nanometers. We're only allowed 3
Oh, yeah.
significant figures, so 1140. Okay. Well, we assume that's the correct answer then.
Yeah.
That's not what we were expecting, but I haven't done these ahead of time. You just, one of the things that we do in my classes, you just do the calculations, and you get whatever it says you get. Okay, we were expecting that to be a different number, but whatever. Okay. Let's have a look at what ozone. So this thing that I just erased is something incredibly important. Ozone uses ultraviolet light as energy during a reaction. One of the things that we learned about endothermic reactions is you have reactants plus energy goes to product. They take in energy. So this reaction is consuming energy on the way in. And ozone uses ultraviolet to be decomposed. This is how it forms a protective layer. The ultraviolet hits the oxygen in the upper atmosphere, turns that oxygen into ozone, and then turns the ozone back into oxygen. And it consumes ultraviolet in both directions. This protects the layer of atmosphere and everything below it, all the way to the ground level, from high levels of ultraviolet. It filters out. Ultraviolet. Okay. So here's a question. What is it? It's a colorless gas. It does have a smell. You might have even smelled ozone. It's not a bad smell at all. It's you smell it if you've been around electrical motors and discharge, electrical discharge. There's a particular smell that comes with that. It's the ozone. It's a little bit sharp.
I almost think of it like it's like a smell of like sterile, like.
Yeah.
Yeah, it's like a very
Yeah.
sterile, like.
Yeah, it's not good for you, but it doesn't smell bad. I mean, some things are bad for you and smell bad. What does it look like? Well, we know some things are, I'm not going to say easy, because it took a leap of faith in chemistry 1 to get here, but dioxygen, O2, is like, hey, oxygen's in group 6. 1, 2, 3, 4, 5, 6. And then I need another oxygen. 1, 2, 3, 4, 5, 6. And I make a bond by sharing 2 electrons between 2 atoms. And now this one has 1, 2, 3, 4, 5, 6, 7 electrons, and 1, 2, 3, 4, 5, 6, 7 electrons, and that's not enough. You need to get to 8. But I got unpaired electrons, so you do it again. And you get this situation where you have a double bond between the oxygens and lone pairs of electrons. Okay. Now do ozone. Ozone is 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And then, what else can I do? 1, 2, 3, 4, 5, 6. Oxygen's in group 6. It has 6 valence electrons. It wants 8 valence electrons. How many covalent bonds does it always make? What's the difference between 8 and 6? It's in group 6. It wants 8. It has 6 electrons. It wants 8 electrons. It needs to make 2 bonds. This is your homework. Tuesday, come back with a rational explanation of what the shape of ozone could be. You already said what you thought it could be, but it's not going to be that because it's too strained. But it does make sense. Okay, the hint here is this is difficult. It's not ordinary. It's not ordinary because this is a high energy molecule. It's not a stable molecule. It's going to do something that we're not anticipating. Difficult. Okay. I have a quiz ready to go for you. I just haven't deployed it because I keep thinking I can add an extra question to that and I should just let it go.